Alright, heck yeah, let's begin. We need this hella complicated equation, you know what I mean, acceleration. Well, you have in the radial direction, and then that's like going out from the radius, and then you have the tangential, you know what I mean, that's like that direction. So you got three components in the tangential, two components in the radial, you know what I mean. Some of these are just the same. So let's just write this one down. So in the radial direction, you got, this is just alpha minus r, no, damn it, no. Okay, so this is the acceleration of the radius going outward. So this is the guys running, so we got to call it r dot, that's the best thing to call it. Our radius plus omega, that's revolutions in radians per second, all that squared. Okay, so and we're just going to say that's acceleration in the radial direction, and now we need acceleration in the what, tangent direction, you know what I mean? So anyway, it's the velocity of the radius. So if the and we're going to get to our problem here. Omega, radians per second, plus radius, wherever the point is, you know, from the origin, and then, if there's an angular acceleration. Okay, that makes sense. Okay, maybe none of that makes sense. That's the whole point of just like, you know, I mean, only a couple of these components actually make sense. But here's the problem. Okay, starting from rest, anyway, the boy runs outward in a radial direction from the center of the platform. Now, just right there, you know, the only person that's going to tackle these problems is like, you know, if you pay like $20,000 a semester to go to college, I don't think we need a boy, you know what I mean? So we're just going to, you know what I mean? Anyway, the runner, you know what I mean? Don't have to be gender anything, and there you go. All right, so the runner runs. The runner runs outward in a radial direction from the center of the platform with a constant acceleration of 0.5 meters per second. Okay, so just right there, do we all know what acceleration is? Acceleration is the change in velocity, change in time. Because if I say, what the hell's velocity? And you're just like, well, we all know velocity. We've all seen Fast and the Furious. But anyway, change in velocity is just change in position, change in time. So these are the two definitions we hella need to know. And anyway, so we're saying that the acceleration of this runner is 0.5 meters per second every second. You know what I mean? Every 1 second. Okay, perfect. Change in velocity is 0.5 meters per second. Every change in time is 1 second. Okay, so we got that part. But the platform's rotating, and that's called theta dot. But no, just radians. And this is going to be, the units on this is radians per second. And what do we get? We get 0.2 radians per second. Now, I'm just going to throw this out. How long before this thing does a full circle? How long? You know, can you do it in your head? Hell no, no one can. But how many seconds to get 1 radian? Oh well, it looks like it's going to be 5 seconds. 5 seconds equals 1 radian. How many radians in a circle? It's 6. So, you know, there's 6 radians equals 1 circle. Now, you know, you can just graduate college. If you know 6 radians is equal to circle, they'll just give you a degree because you know more than everyone else. Alright, so now how many seconds is it going to take? Well, it took 5 seconds to go 1 radian, and a full circle is 6 radians. So it looks like it's going to take 30 seconds. Holy Toledo. Okay, so we got it. So 30 seconds per rotation. How about just revolution? There you go. 30 seconds per rev. Okay, so now we got this. And how big is the friggin' plate? Is it just the Earth? Is this runner just running from the North Pole? Is this just the North Pole? And the Earth sped up hella and can do a full day in 30 seconds? Or is it just a crazy planet? What are we talking about? No, it doesn't even give Doesn't even give the dimensions of this plate. It just says, hey, we got a plate as big as you want it to be. But at the end, it'll make a little bit more sense. Okay, so determine the radial and transverse components of the velocity and acceleration of the runner. Alright, of the runner when t is equal to 3 seconds. Neglect I think we already did that. I think that's why we just called the boy a runner. Okay, there you go. So, alright, so t is equal to 3. That's the biggest parameter right there. Like, hell yeah. Because now, in 3 seconds, you know, let's say he's at the end of our plate. And how far is that? This is the first thing, you know, we don't even need to figure out how it's spinning. We just need to figure out, like, whoa, in 3 seconds, if this runner's going to run on a straight line, you know what I mean? So let's say you do have a plate, but you do a straight line. You draw a straight line on a plate, and then the runner runs that straight line. Okay, and in 3 seconds, how fast is that runner going? Well, that runner started out at rest, so velocity is equal to 0. So 0 velocity here, but guess what? What's his velocity changing? Every second, velocity is going to increase by 0.5 meters per second. Now, just for the Americans, you know what I mean, and I'm one of them, what the hell is 0.5 meters per second? Well, just times 2. Okay, so that's 1. So is that 1 mile per hour? Sure, I'll give it to you. But plus 25%. Okay, what the hell is 25% of 0.5? Well, 10% of 0.5 is 0.05. So we could do another one. That's 20% plus 0.25. Ooh, that's too much. That's too much math. We got 0.125. Okay. So yeah, 1.125 miles per hour. See, it didn't make a lick of difference in this case, but every second we're going to increase by about 1 mile per hour, just a little bit more. You know what I mean? After adding to 8 seconds, we'll have to add another mile per hour. I think we get it. Okay, so in 3 seconds, so in the first second, you were going 0, and by the end of the first second, though, hell yeah, now you so your velocity. So your time is going to be 0, 1, 2, 3. And then your velocity is going to be 0, 0.5, 1.0, 1.5. Okay, cool. So now how do we do distance? You know what I mean? Is there any way we could figure that out? Well, sure. Because in 1 second, you had 0 velocity, and then you had 0.5 meters per second. So what's our velocity average? You know, what's right in the middle? So we'll go velocity average. Well, that's 0.25. Okay, and what's our velocity average? 0.75. What's our velocity average right here? Well, it's 1.25. Okay, so in that first second, just pretend we're going 0.25 meters per second. Okay, well, if we're going 0.25 meters per second in 1 second, looks like we're going 0.25 meters. Okay, and then in the next second we're going 0.75 meters per second. Well, it looks like we're going to add on we're going to go 0.75 meters more, and then 1.25 meters more. But get this, so our position actually is well, at the end of 1, so we're 0, and then 0.25, but then we have to add 0.75 to 0.25, so at the end of 2 seconds, we're at 1 meter. And then we have, at the end of 3 seconds, well, we have to add 1.25 meters. Oh, whoa. So we're 2.25 meters. Okay, so even that, we didn't even have to do anything too crazy. But the other way to do that, if you want to do this real fast with integration, acceleration, well, hell yeah, that's an equation. And here's how you do it. Acceleration of this runner is 0.5 meters per second squared. Well, this is acceleration is 0.5 t to the 0. You know, units are meters per second squared. So now because it's t to the 0, which anything to the 0 is just 1. So, you know, that's just 0. Okay, and then we're going to integrate area. Or accelerate, holy Toledo, integrate 0.5 t to the 0, hell yeah, dt, so now we get velocity. integration of acceleration is velocity, and now we'll get 0.5 t to the 1. Okay, and now we're going to integrate that dt, and then we'll get position. Whoa, just position, which is 0.5 t to the 2 divided by 2, which is 0.25 t squared. Now, did we do it right? Because if we put in a 0, hell yeah, we're going to get 0. We put in a 1, hell yeah, we're going to get 0.25. We put in a 2, well, that's 4. Shoot, we get 1. And then we put in 3, well, that's 9. And I can't do math, but just pretend it's 10. If this was 10, it would be 2.50. But it's 9, so it's just 1 less than that. Oh, hell yeah, 2.25. Whoa, that was some screaming. That's why you make these videos, because we're just guessing. We're just figuring it out on the fly. And I'm going to throw some more time on the clock. Alright, so we got some more time on the clock, and you know what I mean? You can end the video if that was just enough. If that wet your whistle, you're just like, whoa. You know, thanks for going over this acceleration thing all the time. And thanks for just doing a simple little chart. That made sense. Because the crazy thing is it's the average velocity. You know what I mean? If I say I'm going 0 miles per hour right now, but in 1 second, I'm going to be going 0.5, 1 mile per hour. Well, how many? Well, that don't make sense. That don't make sense at all. But anyway, if I was going 1 meter per second, let's say I was just going 1 meter per second, and I started out going 0 meters per second, but by the end of the first meter, I'm up to speed of 1 meter per second. Well, how much distance did I travel? Did I travel a meter? Well, no. To travel 1 meter in 1 second, your average velocity has got to be 1 meter per second. But your max velocity is going to be 1 meter per second after you got up to speed. And so you're going 0 here and you're going 1.5 here. So the actual or you're going, man, I'm just confusing myself. Because in 1 second you were going 0.5 meters per second. Let's do that. 0.5 meters per second. So I'm at rest. And then in 1 second, I'm going 0.5 meters per second. Let's say I was just going 0.5 meters per second. Okay, so I was just going 0.5 meters per second, and I did that in 1 second. How much distance did I travel? Well, 0.5 meters. But if I started at 0 and then slowly increased my speed to 0.5 meters per second, well, what distance do I travel? Well, you got to find the average velocity, which it's real easy. Velocity average is just a 0.25 meters per second, and it looks like you went 0.25 meters per second. Okay, I think we get that's not even the hard part of this problem, but that's good. And how big is our plate? Holy Toledo! We're only talking about 3 seconds, and our plate's only 2.25 meters. That sounds like 10 feet. You know what I mean? Well, it looks like our plate is 10 feet in radius. So the radius is 10 feet. It's 20 feet in diameter. All right, so you got a 20-foot spinning disc. Hey, that's pretty decent. That's pretty decent. All right, so and now it's going real slow. So in 3 seconds, like I said, in 5 seconds, it's going to go 1 radian. What the hell is 1 radian? Well, if you want to graduate with honors, 1 radian is approximately equal to 60 degrees. You know what I mean? It's 57.7, or, who cares? Because 0.5 radians is basically 30 degrees, and that's even more accurate. You know what I mean? So if you know those two, you can graduate with honors. All right, so you're saying in 3 seconds, this person's not even going to go 1 radian? Hell no. So let's say the runner was going 0.25 seconds. It would go 30 degrees. You know what I mean? But we're only going, we're like 25 degrees. So it literally, starts going this way, and in about 25 degrees, it'll be in 3 seconds at the end of the disc, and then it wants to know determine the radial and transverse components of the velocity and the acceleration. Okay, fine, fair enough. You know what I mean? Well, isn't the velocity, like he's running this way, So right here, we already said he's going 2.25 meters per second. Double it. Looks like he's going 5 miles an hour. So right here, he's going 2.25 meters per second that direction. Okay, yeah, we got it. And then he's also going velocity. Well, he's getting wung around this circle. Not very fast, but the velocity is equal to radians per second times radius. Because if we know the angular rotation, which is omega is angular velocity. If we know angular velocity, well, that's in radians per second. And if all you have to do is, anytime you hear the word radian, just times radius and you get something normal. So angular velocity, radians per second, times radius, well, that just gives you the normal friggin' velocity that is getting flung that direction. Okay, so 0.2 radians per second times the radius, which we said was 2.25. Okay, so it's going to be a pretty small number. 0.2 times 2.25. Alright, so we just get 0.45 meters per second that direction. So he's getting, like I said, he's getting wung pretty slowly. Like, well, yeah. He can run this way about 5 times as fast as he's getting wung that way. So there you go. So there's the velocity going that way. Got it? 0.45 meters per second, or about 1 mile an hour. You know what I mean? And then he's going about 5 miles an hour running that way. We can imagine a runner running 5 miles an hour. It's pretty slow. Okay, so all right. But I think the what's the components of the acceleration, though? You know what I mean? Like his velocity at that point, yes, is 2.25, and his velocity at this point is 0.45 meters per second. Now, how much is his velocity and acceleration changing? Well, like we said, we had time 2 right there. So how about this? This was his velocity tangential at 3 seconds. What's his velocity tangential at 2 seconds? Well, he'd be only the runner's only 1 meter away. Yeah. So it's 1 meter. So it's radians, 0.2 radians per second times radius, which is 1 meter. Okay, so that's 0.2 meters per second. So yeah, so his velocity. Okay, so what did the velocity? So now we got, and this ain't very accurate. But let's say we wanted to find the acceleration from 2 seconds to 3 seconds. Well, isn't the acceleration tangential just the velocity tangential at 3 minus the velocity tangential at 2 divided by the change in time, which is just 1 second? Okay, sweet. So that's going to be 0.45 meters per second minus 0.2 meters per second divided by 1. Oh, okay. So it's just going to be 0.25 meters per second. So you're going to change your velocity by 0.25 meters per second, or about a half a mile an hour, every 1 second. You know what I mean? Or 0.25 meters per second squared. But don't write it like that unless you want to show people you don't know what you're talking about. Shoot. Man, I got food ready. Gotta eat some dinner. Okay, put some more time on the... Man! Alright, man. Hopefully the battery lasts too. Holy Toledo. Okay, so is this accurate at all? The acceleration in the tangential direction at 3 seconds is 0.25? Hell no. Because we averaged it from time 2 seconds to 3 seconds. We found that. What you really want to do is find the change in velocity, you know what I mean, from like 2.9 seconds to 3 seconds. Now, could we do that? Sure. Because what's our position at 2.9 seconds? Well, that's a 2.9 squared times 0.25. Okay, well, so we're going to store that as, store that. So that would be 2.0125. That's our position. That's our meters times so that's our radius times radians, which is 0.2 radians. So times 0.2. Hell yeah. So we get 0.4205, and our actual was 0.45. So we subtract those. So 0.45 minus that second one, and then we divide it by 1/10 of a second. Okay, so our acceleration tangential at 3 in the tangential direction is 0.295 meters per second squared. Okay, and instead of 0.25, it's 0.295. So it's pretty close to 0.3 meters per second squared. But yeah, okay, perfect. So it's, I'm just going to stick with 0.295 meters per second squared. And now what do we need to know? So that was in the tangential direction. What's the acceleration? What's the acceleration in the radial direction? Well, you know what I mean? It's just 0.25. So the acceleration in the radial direction is 0.5 meters per second squared, because they already give it to you. He's running at a constant speed. But we have to double check with this equation. That's why I'm just trying to use what I know, because it says the acceleration in the tangential direction, that's here, acceleration tangential is equal to, well, it's the velocity. You also have to add the velocity. So the velocity at 3 seconds, well, shoot. The velocity at 3 seconds, that was 1.25. No, the velocity at 3 seconds was 1.5. Okay, so you got to go 1.5 meters per second times 0.2, and then you got to times 0.2. So you're adding, shoot, so that's 2 times 1.5 times 0.2, that's 0.6. So that component is 0.6 meters per second squared. And we said we came up with, in the tangential, 0.3. So the acceleration in the tangential direction is really close to 1 meter per second squared, because you have to add this in. Now, I haven't done a proof for why you have to do this, besides just knowing this equation and don't forget about it. You know what I mean? Because right here, what's the oh, no, I think we tried to incorporate it. Yeah, because we said, I don't know. Yeah, we said you had a change in velocity. Yeah, we kind of did that. We kind of did the change in velocity. But we only did the, man. So I don't know. You know what I mean? So this is the angular acceleration of the disk. It's not accelerating, that's 0. So yeah, I'm just, you know what I mean? So I threw in my numbers, but I only used the velocity in the tangential direction. I only said the velocity in the tangential direction was changing, but guess what? The velocity, if the velocity is changing in the radial direction, that also influences the tangential direction. I think it doubles it. You know, I think that's where this 2 comes from, but don't quote me on that. You know what I mean? That's why. So when I did it right here, the answer would be 0.6. It wouldn't be 0.6 plus what I got. It would just be 0.6. So I got 0.3, you know what I mean, basically, and if you do it like this, you get 0.6. So, anyway, I'm not confusing you, but if you just want the equation, there you go. But if you're doing what I'm doing, I'm trying to do the most basic problems to figure out, hey, can I even see this acceleration, you know, from a very practical perspective? And I still can't, but anyway, I guess I double it. So now the acceleration in the radial direction, well, yeah, I guess I get it, because, you know, your acceleration has a component, you know, you should just be flying this way, but no, you're actually changing your velocity back, you know, to actually main on the outside of the disk. So I got that, so that's that component. And if the radius is actually accelerating, well, yeah, and let's say 0.5 meters per second squared, that's what the runner's running. You know, minus the radius, well, is going to be 2.25 and 0.2 squared. So that's pretty small. 0.2 squared times 2.25. All right, that's just minuscule, but it's a 0.09. So not quite minuscule, but 0.5 minus 0.5 minus, yeah, so the acceleration in the radial direction, this is going to be 0.41 meters per second squared. Oh, that's kind of interesting. You know what I mean? So and that just makes practical sense. This runner, you know, let's say the thing wasn't spinning. Well, yeah, they're accelerating at 0.5 meters per second. Pretty incredible. And until they get up to about 12 or 15 miles an hour, they can't accelerate no more. But anyway, for at least 10 seconds, you can accelerate by 1 mile per hour. Sure. And we're just, anyway. But the fact that he's accelerating this way, let's see. And then moving that way, it's weird because, you know what I mean? If he was trying to get, so if he's trying to get right there to this line, this is perfect. And let's say in 2 seconds he can get to this line, and in 3 seconds he's got to get to this line. Well, yeah, we said, sure, he did it. But this is just an imaginary line in space. All right, this is just going to blow your mind. But guess what? It's going to take him a little bit more time to get to this line. Just pretend this disc goes on forever. Because the second he gets here, he's not right there. This runner is just over here. And he's got to make up this distance right there. So what's that distance that he's got to make up? Well, that's because there's an acceleration, change in velocity back to the radius. So this is your classic r omega squared. I'm not going to go over it in this video, but hell yeah. If nothing's changing, what's the acceleration towards the radius on this disc? You know what I mean? Well, it's this component. And there's no change in radius. This would go to 0, and then you just have that. All right, so I'm satisfied with drawing this imaginary line right there. And even if this thing's spinning, you know what I mean, this radius, he's now over here, and he's got to go just a little bit farther to actually get to right here. So that's why there's a minus component. And I'm just going to leave it at that. So we came up with the answer. The acceleration is the only one I'm interested in. See if I was even right. 0.41 meters per second in the radius direction, because it's 0.5 minus just a little bit. We get that. And then the acceleration in this direction, well, you know, we just went to the equation. 2 times the velocity at 3 seconds, which was 2.25 meters per second. No, the velocity at 3 seconds was 1.5 meters per second. That was the velocity at, velocity at 3 seconds. 3 times 0.5, that's 1.5 meters per second, times radians per second, 0.2, times 2. And then you get the acceleration in the trend. But I still don't know, I still haven't derived this one to be like, oh yeah, I got it. But anyway, I don't, you know what I mean? I think we're on our way, and I want to make more of these videos. And this one I'm going to be done with. But hey, thanks for joining me. And that's a video.